Depth first search is one of our graph traversal methods. Depth first search was devised by John Hopcroft and Robert Tarjan back in the 1970s. And in this particular algorithm, each vertex is visited, and then all the unvisited vertices adjacent to that vertex are visited. Okay, so if the vertex has no adjacent vertices, or if they've all been visited, then we backtrack to the previous vertex, right? This can continue all the way until we get back to the initial vertex for where the traversal started. If any vertices remain unvisited at any point, then they would be explored once the backtracking took place, and we would go off and we would explore that. So I mentioned backtracking, so that should automatically bring to your mind the notion of recursion, and it so happens that depth first search is often implemented as a recursive algorithm, and you see that the recursive form is really very simple. Simply takes a vertex to start from and marks that vertex as visited, and then for each adjacent vertex to the vertex that came in, we basically, if it's not been visited, we call the function recursively. So that's a very clean looking recursive function. Here's one that is a little busier because it's got some comments, but it's basically the same thing, where we take in a graph and a vertex and we pre-visit, as they in this particular method they do a pre-visit and they do a post-visit. That's not always necessary. That's basically going to be application dependent. But the idea is that we mark that vertex as visited, as we did in the previous slide, and then we go through all of the adjacent vertices, and if they're not visited, we call depth first search recursively with that new endpoint. We will now walk through an iterative version of the depth first search algorithm. So a few things to note. First of all, we've got the graph that we're operating on, and we will begin at vertex A. So when we call this particular function, we'll call it with DFS capital A, and that will be received by the parameter S. We immediately load that. We allocate a stack and we load that vertex onto a stack. So we've made a choice here that we will push the vertices onto the stack in reverse alphabetical order. So for instance, when we visit A is connected to B, D, F, and G. We will push G first, and then F, and then D, and then B. So we will keep that method throughout, just to be consistent. You don't have to do it that way. You can do it in forward order, or you can do it in some random order. But in order to keep things organized, we will push the vertices in reverse alphabetical order. We will list the processing, which is a result of the statement that's highlighted. We will list that processing on the bottom right of the screen to show the actual order in which things are being processed. So then, without further ado, let's move on to this example. So DFS A is called. A inhabits the parameter lowercase s. Capital S is a stack, and we have pushed A onto the stack, and so that is our first stack image. And since A is on the stack is obviously not empty, so we will pop we will pop the value from the stack. And since A has not been visited, we will process A. So we will begin by writing A here. And we can now mark A as visited, and I will do so on the graph here. So a check mark by the vertex means it's been visited. And now for each edge that connects to A, you notice that A was popped from the stack and it was renamed vertex lowercase v. So for each vertex that is connected, for each edge, we will look at the other endpoint. That's what this means. So this is A here, and this is everything else that connects to A. And if that vertex is not visited, we will push it onto the stack. And as we mentioned, we will push things onto the stack in reverse order. So let me remove A from the stack, and we will go on then. So first we will push G onto the stack. And so that's this one. And then we will push F onto the stack. We will then push D, which connects to A also. And finally, we will push B, and those are all the edges that emanate from A. So our stack now looks like this. And at this point, all we've done is process A in this case, and we've output that on the process stream. And now we go back to the top of the loop and we pop the next value. So at this point, we will pop B from the stack. So I will remove B, and then I will show the stack here. So G is here, F is here, and D is still on the stack. And now let's look at it. Since B has not been visited, we will process B. Okay, so we'll add B to the output stream, and we will mark B as having been visited. And at this point, for everything that is connected to B, we will go through and we will push those onto the stack in reverse order. So at this point, everything that has not been visited. So B connects to A, but A has already been visited. So we will not push that onto the stack, but we will push both E and F onto the stack. And as you'll notice, F is already on the stack, and so F will be on the stack twice at this point. So since we're doing it in reverse alphabetical order, we will push F onto the stack and then push E onto the stack. Okay, and then there's nothing else connected to B. B only connects to A, which has already been visited, F, and E. Okay, and at this point, the loop iteration terminates, and we will go back to the top, and then we pop E. And so I'll redraw the stack, G, F, D, and F again. E has not been visited, so we will process E by outputting it on our output stream. And we will mark E as visited. And now everything that is connected to E that has not been visited, we will now push onto the stack. And you see that E is only connected to B, which has been visited, but it is also connected to G, which has not been visited. So we push G onto the stack again. So there are two instances of G on the stack, one here and one here. And at this point, we're done with this iteration. And so the next iteration is to pop G off. And when we do, I will redraw the stack, and then we will do our processing. Okay, so there's G, there's F, there is D, and there's an other F. Okay, and at this point we just popped off G. G has not been visited. It's not marked here with a check mark, so we process G. So here's G, and we mark G now as visited. And then everything that is connected to G but not marked as visited, we push onto the stack. At this point, there is nothing new to push onto the stack. Okay, and so we're ready to go to the next step. So we pop F off, and we've got G and F and D. Okay, and F has not been previously marked as visited, so we enter the if statement and we process F, and we mark F as visited. And now for each other vertex that is connected to F and not visited, we will push those onto the stack. So F is connected to A and B, which have been visited, but F is also connected to D and C, and we've committed to putting those in reverse order. So we will push D and we will push C onto the stack. Okay, and this iteration is over, and so we go back to the top of the while loop. Stack's not empty, so we pop off our next one, which is C, and we'll redraw the stack. There's a G, an F, and two Ds. Okay, and we just popped off C. C has not been visited, so we enter the if statement and we process C. So we'll output it on our output stream, and we'll mark C as visited. Okay, and we will now look at the things that C are connected to, and if they've not been visited, we will push them onto the stack. Well, C is only connected to F and to H, so H is the one that has not yet been visited, so we will push H onto the stack. And at this point, the iteration terminates, and we go back to the top of the loop, and we pop H off. And I'll reconstruct the stack: G, F, D, and D. And H has not been visited, so we process H. So we put it on the output stream and we mark it as visited. Okay, and so now everything that is connected to H, if it has not been visited, we want to go ahead and to push that onto the stack. There is nothing to push onto the stack at this particular point, so we're done with this iteration. We will now pop off this first ugly D and redraw our stack. So there's G and F, and now there's only one D left. We look at D. D has not been visited, so we process D, and we mark D as visited. And now for every other node that is connected to D, if it has not been visited, we will push it onto the stack. Well, as we look at our graph, every node has been visited, so there is nothing to push onto the stack. Okay, so we will pop D off, and we'll end up with just G and F. And we just pop D off, but D has already been visited, so we don't enter this if statement, and we immediately go back to the top of the loop. We pop F off, and that gives us just G remaining in the stack. But F has been visited, so we do not enter this loop, this if statement, excuse me. So we don't enter the if statement, and we go back to the top, and the stack is still not empty. We pop the last element of the stack off. And at this point, we just pop G off, so we still have to go through the code. We enter the loop, we pop G, but G has been visited, so not visited is false, so we don't enter this if statement. And at this point, the iteration terminates when we go back to the top of the loop, and the stack is empty as shown in number 11, and thus we have performed depth first search on this graph.